Alright guys, so I'm just going to start. If you are finishing up 3, that's fine, but I want to kind of show you the process as I can. So this is the only information we are given. We're given some more information to build the problem, but that's it for the initial, and that is 50 milliliters there. You know it's an acid-base reaction, so they have to react. If they have to react, it means they have to be consumed. It's a BDA versus kind of an ice method. So the very first thing you had to do was figure out the molar mass, right? So what did you guys, everyone should have got that part. How did you start? How did you get the molar mass of the weak acid? So thank you, stoichiometry. So you have to start off with your sodium hydroxide information. So starting off with your 0.03523 liters, because this is the equivalence point. So whenever you have the moles of the sodium hydroxide at the equivalence point, that equals the moles of the acid at the equivalence point. So that logic should give you moles of acid. And then you're going to use the grams to figure out grams per mole for the molarity. So this is your sodium hydroxide, 0.2211, and this is the information that they would want to see on the AP exam. So I'm trying to model for you, liters, you get your moles of sodium hydroxide, and then you show your mole ratio between moles of acid and moles of base in the actual process of stoichiometry. This gives you 7.789 times 10 to the negative third moles of acid, and that is going to be used to find the molar mass. So this information, they give you 1 point for this, and then 1 point for the process of molar mass, so taking grams divided by moles. And so we got 176 grams per mole. Yes? That was a 2-point problem. Maybe I have to think, it might have been a 3-point problem, because you probably got a point for this information indicating the 1-to-1 mole ratio, 1 point for your moles of acid, and 1 point for your molar mass. Okay. B gives you a lot of just random information, right? First it tells you at 20 milliliters of sodium hydroxide, it's going to be 4.23 pH. Okay, and then it says find the acid dissociation constant. What is it asking for? Ka. Right, so you have to know acid dissociation constant means find Ka. But this is not the information I need to find Ka. So the very first thing I did was just set up the Ka expression, and I know Ka expression is the dissociation of the acid. But when the acid dissociates, not even thinking about the reaction here, not even thinking about the sodium hydroxide, when an acid dissociates, it makes hydronium and A-, and it has so reactants or products over the reactant, it has the HA here. So we know that these are the 3 pieces that we need to find the Ka constant. Which one can I immediately find? Say again? I cannot immediately find it at this point. Right, I can find the hydronium because I have the pH given to me, so I can go straight to finding hydronium concentration by taking 10 to the negative 4.23. That gives me 5.88 times 10 to the negative 5th molar. So that's hydronium. So I'm just going to kind of leave that there hanging out because I really can't do a whole lot with it right now, but I know it's going to go in there. So then your job is to figure out how do I find the HA and the A- concentrations at this point, because it's past the initial, so I can't use the initial concentrations given. I can't do a whole lot, but I do know that they react, right? So I know that it's HA plus sodium hydroxide yields water and salts. I know that's my reaction. How much of them do I have to begin with, and how much have been used? Well, at the beginning, I have how many moles of this guy?
0.07789.
So we already calculated that in part A, right? So I have scientific notation, so I'm going to stick with that for now. 7.789 times 10 to the negative third moles of that. And then at this very point, how much sodium hydroxide do I have, or how can I figure that out? At this point. Any takers? 0.2211. Right, I have 20 milliliters of 0.2211 molar sodium hydroxide, so how do I get moles? Right, so I'm basically doing M times V to get moles right here, and when I do multiply that out, it is 4.422 times 10 to the negative third moles of that base. Okay, so who's definitely left over in excess here? Right, the HA. And you already knew that, because have we reached the equivalence point yet? No, the equivalence was like 35 milliliters. We're only at 20. We know the excess is going to be HA, and we know that when we react it, we're making A minus through the formation of the salt. So we know that this is going to be an excess, so I'll just set up a BDA, and you don't have to show every bit of work here. I actually condensed mine to like a tenth of this, but you know that all of this is going away, right? So I actually don't even really worry about it. I don't have to show every step here, but I do know that this is subtracting in a 1-to-1 mole ratio, 4.422 times 10 to the negative 3. And I know it's adding on this side in the same ratio, 4.422 times 10 to the negative 3 moles. These are the only two things that are important to me. That's all. That's why I'm only considering those. This is 0. This is excess of 3.367 times 10 to the negative 3 moles. And this is, making this amount of A minus. Okay, so I'm really close to the molarities of both of these species at this 20 milliliter point. So what do I do from there? So I have the moles of the acid remaining. This is HA. I have the moles of product made, which is A minus because it's in a 1-to-1 ratio. Divided by what? How many liters? Is it 0.26?
I mean,
So it's how many milliliters of the acid that we have to begin with? 50 right there, and then plus the 20 that we have in this reaction. So 70 total is our total volume, and that's what you're using to get the total or get the final molarity. So divide that by 70 milliliters, which is 0.7 liters. Divide that by the liters, and these will give you your concentrations that you'll be then plugging in unless you do Ka. So this is 4.81 times 10 to the negative 2 molar. And then your A minus ion is 6.317 times 10 to the negative 2 molar. Okay, so now what do I do? With all this mess that I've just calculated, maybe remind yourself of what the dang question was.
The concentration that you found first, the H, and then the concentration of A over concentration of HA.
Okay, so I'm doing hydronium times A minus over HA. So I'm not going to write all my values out. You guys can do that. But when I plug everything in for my Ka values based off my setup previously, you get 7.73 times 10 to the negative 5th as your Ka value. And again, this Ka value represents the dissociation of the acid, nothing to do with sodium hydroxide, right? So that's a mistake that once you start seeing a reaction, you're like, oh, any reaction, I do products over reactants to find a Ka. No, it's very specific to the dissociation of HA in water. So that's why we have that. Okay, so we got Ka value for our monoprotic acid. Part C. Look at that one and tell me, give yourself maybe 30 seconds to a minute to look at that. Part C. And tell me what you think.
it's just going to be the inverse of like going over it. No.
Think again. I guess, let me just read the question.
Oh.
Okay, hold on. Think to yourself. All right, raise your hand when you know what to do on part C. Okay, put your mic on. You keep going. You've heard me. Part C says, calculate the equilibrium constant for the reaction of a sorbic ion with water. So what are you probably doing first? Kind of your normal first step.
Right on.
Right, without the anion reaction with water, right? So A minus is our anion, a sorbic ion. At reacting with water, what happens? It really has no choice. It gets what?
HA.
Right, it gets an H plus. If there's really no choice here, it has to gain an H plus. So HA forms in hydroxide, right? Hydroxide forms. So what's your next thought in your head? I'm trying not to tell you. I'll see what you can do. Anybody? Not Kevin. What the heck is happening? Okay, so the other thing's acting as the, so if that is acting as the base, what do you have to do? Thank you. So you have to find the KB from Ka. Okay, this is not simply the reverse of the dissociation reaction. The dissociation reaction had HA plus water yields A minus and hydronium. So the reverse of that would have hydronium and water in it. Well, this definitely is not the reverse of that, and that's one of the misconceptions on this one. Because once you find Ka, you're like, hey, they just reverse the reaction, 1 over Ka, and flip it. No, that's a big a part where people have a mishap. So this one, you write your, oh, from the bottom, you write your reaction out, and you realize it's not this just reverse, it's actually the Kb of the Ka that we found in part C, and then move on from there. So how do you find a Kb? Right, Kw divided by Ka, and what is Kw? But what's the constant? 1 times 10 to the negative 14th divided by our Ka value that we just found in part C. And so that value is 1.29 times 10 to the negative 10. That's useful later on. You'll notice at FRQs, they feed you the answers that you need for the next part, but you have to see it. Like, I'm reading between the lines thinking, I used part C and part D. I mean, sorry, this was part D, by the way. Yeah. I used part B and part C. Maybe I'll use part C and part D. Maybe. So let's think about it. pH of a solution at the equivalence point of the titration. All right, so you tell me your first, maybe two steps. Whenever you're ready.
Find the molarity of
A minus. Okay, so if I find the molarity of A minus, that's a point I need, but I can't get there directly. What do I need to do? Let me do something else first. Molarity is consisting of what and what? Moles over liters, right? I can easily find liters. I know the volumes at the equivalence point. That's fine. So what do I probably need to find first? Moles of A minus created at the equivalence point. So I like the backtracking nature of this. Because I know if I have the A minus, I can eventually find the pH of that by salt hydrolysis. But I need to find the moles of A minus. Well, how do I do that? That was moles at 20 milliliters. This is at the equivalence point, which is at 35.23 milliliters or something like that. So I'll kind of help you out here, but I'm trying to back off and let you guys think. I know it's really difficult sometimes, but you know that this is making salt and water, right? We know at the equivalence point what's true about these two guys.
Wouldn't they be the same?
Yeah, they're the same. So if these two are equal, so I'm not going to do all the math, right? So we know these are equal, and they make a 1 to 1 mole ratio of this. So how much of this is made?
The same.
The same that was there. Well, we know how much is there, how much HA was present in the very beginning, guys. I hear you, Chizro. Say again. 7.789 times 10 to the negative 3, right? Negative 3 moles. So we know how much of the HA was present. So we know the sodium hydroxide has to equally cancel it out. We know that we're making the same amount of sodium A minus. So this is the moles of A minus, all right? At the equivalence point. And I could have done a whole dang BDA table, but nobody's got time for that, right? So BDA, in our head, we just did it. This 7.789 times 10 to the negative 3 needs to be divided by what, though, to get the new molarity? And what is that? 50 plus the 35.23 that it said was used at the equivalence point. So 85.23 to 0.08523 liters. That gives us a concentration of 9.1388, and I'm extending my decimals because I don't want to have any rounding error. That's the molarity, 9.1388 times 10 to the negative 2 molar. Okay, and this is where you come in because you're comfortable with finding pH of anything. I can give you literally anything and you can find the pH of it because you've got all these methods of solving for that now. How do I find the pH of an anion? Itself is inherently not an acid or a base, correct? Well, that came from a salt, right? So this salt right here. So let me back up. How do I find the pH of a salt? I do it. Split it up, and that's kind of what I did. I have sodium ion and anion. Who's the important one? In this case, anion, because sodium ion, when it reacts with water through salt hydrolysis, what happens? It makes sodium hydroxide, 100% dissociates back, so no reaction. So what do you do with this? I got it
React with
separated.
water.
Add it with, react with water. So I'm doing salt hydrolysis. What does it make?
HA and OH minus.
Huh. I've seen that before.
Yes.
Yes, in part C. Then what else do I already have for part C? The Kb value, right? I have the Kb. So really, I'm setting up an ice box. I have my concentration, 9.1388 times 10 to the negative 2. I have 0 of both of these products initially. I subtract x, add x, add x. So then I know my Kb value was 1.29 times 10 to the negative 10. And I know that equals x squared over over 9.1388 times 10 to the negative 2 minus x. All right, so you're good from here. You solve for x, you will neglect x. I checked it earlier. It's 3.7 times 10 to the negative 3%. It's totally negligible. So the x is equal to 3.4 times 10 to the negative 6. And why is that relevant? Who is this?
Concentration.
Of hydroxide, right? So this is hydroxide. And then from there, you'll do pH is equal to 14 minus the negative log of 3.4 times 10 to the negative 6, which is your KOH here. And that's like 8 point something. 55. 8.5. Right, that's a doozy, okay? But every piece of it you know how to do. It's just you need to find a way to start the problem. Don't let yourself just sit on and be like, hey, I don't know what to do. Start something else. Go with what you know. Because none of this stuff really came from my head. It came from the paper. I had one piece of information to start with, and a lot of times you only have one thing you can do with that information. So just do it. Okay? That was a hard one. I want to do that one for you. You guys have 1 through 5 to do. Keep working on those right now.
Are we doing all of them?
Yeah, because I was hoping you guys would get 3 and 4-ish in class. You still have 15 minutes left in class, so work on it.